Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 2.1, Linear Differential Equations. In Chapter 2.1, we will begin to outline the algebraic structure of linear differential equations. We will introduce linear operators and the superposition principle for linear homogeneous equations. We will then present the important non-homogeneous principle, which gives us the form of solutions for non-homogeneous linear differential equations as the sum of homogeneous solutions plus any particular solutions. This is a great section for us to look at. It gets us started on methods for solving differential equations. Let's start off our lecture today with some definitions. First one, a first-order linear differential equation can be written in the form y prime plus p of ty equals f of t. And what I want you to see of in this equation is the form where we have put all of the terms containing the variable y on the left-hand side. And then the right-hand side will be terms that do not contain the variable y. The second definition is a second-order linear differential equation can be written in the form y double prime plus p of ty plus q of ty equals f of t. And again, I'd like to emphasize in this form, we've positioned all of the terms that contain the variable y on the left-hand side, and then all of the terms that do not contain the variable y are on the right-hand side. In general, a linear differential equation is of this form. I won't read all of this out, but it could have many terms. All of the terms containing to a y are going to be on the left-hand side, and each of the terms could have its own coefficient. And then again, all of the terms that do not contain a y are on the right-hand side. In our class, we are going to be focusing on first-order and second-order linear differential equations, so ones that look like the first two types. Recall other definitions. We said that the order of the dE refers to the highest derivative that's present in our differential equation. Our differential equations must be linear in the variable y. So no y squareds, y cubes, sine of y, or square root of y will appear in our differential equations if they're linear. The functions p of t and q of t are functions of the variable t only, and they need not be linear. So I'm fine if I see a t squared or a cosine of t. Those do not have to be linear. If f of t is equal to 0, so we're saying if this right-hand side of our dE ends up being 0, then our dE is referred to as homogeneous. Otherwise, the differential equation is referred to as non-homogeneous. These terms are going to be important because it's going to help us determine how we solve a differential equation. So here's a short exercise. I would like to be able to classify each of the following DEs based on their order, linear or nonlinear, homogeneous or non-homogeneous, variable or constant coefficients. We're talking about the coefficients of our y variable here. So let me start you on the first one. Our first DE, y prime plus ty equals 1. If I were to classify this, I'd first talk about its order. And so the highest derivative that we see is the first derivative. So this is a first order. Is it linear or nonlinear? So now I'm looking at the y terms, and I'm noticing this y prime. It's a ty, where t is your coefficient, but it's just y. It's not y squared. This would be a linear DE. Because the right-hand side is not 0, we refer to it as non-homogeneous. The last portion, we're talking about the coefficients, and we're asking, are the coefficients variable coefficients? Do they change, or are they constant? So now I'm looking at the coefficients of y prime and the coefficients of y here. And so because the coefficient of y is a variable, even though the coefficient of y prime is 1, it's a constant, but because this t on y changes our coefficient, this says that our differential equation is going to be a variable coefficient. Okay, and I'd like to give you a moment to classify the remaining 4 differential equations I have here for you. So pause the video for a moment and classify these last 4 differential equations as or with these 4 classifications I have. I'm going to do this also while the video is paused, so when you come back, you'll see all of the answers presented for us to check ourselves. I'll see you in a moment. Okay, let's see how we did. So I put the answers for the remaining 4 differential equations for the classifications of them. I'm hoping you're checking your answers real quick. One of the ones I see that often get students is D. When we're talking about whether it's homogeneous or non-homogeneous here. And here you'll notice I said it was homogeneous. So remember, when we're talking about differential equations, we want to write them in the form so that all of the y's are on the left-hand side. And in this one, all the y's are not yet on the left-hand side. So you can imagine if you were to rewrite this differential equation, this one would actually look like y double prime plus y minus the sine of y equals 0. And now in this form, we can see that all of the terms containing y's are on the left. The right-hand side are the terms that do not contain y. It's only a 0. This 0 is what tells me this is a homogeneous differential equation. Notice I also said it was nonlinear. And the reason I said it was nonlinear was because we had this sine of y term. And we're not allowed to have nonlinear terms in y. Now, I didn't have a problem with E where it said sine of t, though, because when we're talking about t, t does not have to be linear. Okay, now I'm emphasizing this because in this chapter, this section 2.1, we're only going to be talking about linear differential equations. So we're going to be focusing on A, B, and E. Well, actually, we won't talk about E because E is a fourth order, and we are sticking to first order and second order differential equations now. But these are the only ones I'd be able to talk about. Okay, let's add a little bit more theory to our discussion. And I want to introduce linear operators. The linear operator of a differential equation is obtained by isolating all terms in y and its derivatives on the left side of the differential equation. If the left side now has the form prescribed by equation 3, then the linear operator is exactly the left side of the DE. Thus, in the examples above, we can write the three linear operators for A, B, and... Oh, and I said A, B, and C. I don't think I mean C. So let's change this. If I look back for the linear differential equations, I think we said it was A, B, and E are the linear differential equations. So if you could, let's change this. This should not say C. This should say E. So for our linear differential equations, A in our previous page was this one. I have all of the terms containing y on the left-hand side. That makes this the linear operator. So the linear operator is L of y is y prime plus ty. Similarly for B, all of the terms containing y are on the left-hand side. This is the linear operator. E. Here, all of the terms containing y are on the left-hand side, so that's the linear operator. So this allows us to represent linear differential equations in a shorthand notation. Instead of writing y prime plus p of ty equals f of t, I can just write L of y equals f of t. So I guess in this first problem up here, this one could be written as L of y equals 1. The second one would be L of y equals 0. And this last one would be L of y equals sine of t. Now we're introducing this notation for a couple of the theorems that I'm going to present. Let's first talk about the superposition principle for linear homogeneous differential equations. And I really want to emphasize here that we're talking about linear differential equations only, and we're talking about homogeneous differential equations only. So if you have a different type of differential equation, which we will talk about later, this theorem will not apply. Now this says, if u of t, u1, and if u2 are any solutions of the homogeneous linear differential equation, meaning they produce 0 when you evaluate your linear operator at them, because it's a homogeneous solution. So if u1 and u2 are individually solutions to the homogeneous linear differential equation, then so is any constant multiple of them, meaning k times u1 is also a homogeneous solution. Maybe I should have called this k1 is a homogeneous solution also. Similarly, k2 is also a homogeneous solution. So multiplying these do not change the fact that they'll still be solutions. Maybe I should emphasize in here where K1 and K2 are constants. Similarly, so is the sum going to be a solution. If U1 is a homogeneous solution and U2 is a homogeneous solution, the sum of these will also be a homogeneous solution. Now, putting together 1 and 2, then we will also be able to say that so is any linear combination. So we'll have some multiple of U1 and some multiple of U2 added together will still be a homogeneous solution. Let's practice this idea a little bit. Consider the second order linear homogeneous differential equation. Again, it's second order because of the second derivative that's present. And it's linear because all of the terms on the left-hand side are not raised to any powers or any square roots or signs. These are just linear terms in y. And it's homogeneous because the right-hand side is 0. So we want to verify that each of these are solutions to the homogeneous DE. So let's look at the first one together. Y equals e to the 2t. And I want to verify that this is a homogeneous solution of y double prime minus 4y equals 0. And the way we do this is we evaluate the DE at this proposed solution. So stick it in for y in all the places that y appears. And we're being asked to verify that this indeed equals 0. So we'll do some calculus here. So we'll start with the derivative terms. We have to do 2 derivatives. Of course, you can do this any way you want, but just for teaching it right now, I'm going to do this in pieces. And so I'm going to take a first derivative. If I take a first derivative of e to the 2t, then I'll have 2e to the 2t, and I've left one derivative behind. So the derivative of e to the 2t is e to the 2t times by the chain rule, this 2. Minus 4e to the 2t. And now let's take the derivative again of 2e to the 2t. So this will be our second derivative. The derivative of 2e to the 2t is 4e to the 2t. Notice then that both of these terms are identical, so they cancel. And this is a solution to the homogeneous differential equation because it satisfies it. We'll have to do the same thing for our second proposed solution. Y equals e to the negative 2t. And again, we're going to evaluate our differential equation at this proposed solution to verify that it really does give 0. So plug it in both places. And we want to verify this really does equal 0. So if we take a first derivative, leaving one of the derivatives behind, the derivative of e to the negative 2t is e to the negative 2t times by the chain rule, your negative 2. If we take another derivative of negative 2e to the negative 2t, we'll get another factor of negative 2. So it'll be 4e to the negative 2t minus 4e to the negative 2t Notice that this does equal 0, as each of our terms are the same but opposite in sign, so they'll cancel. Means this is the solution. Now we would like to verify the superposition principle by showing that this linear combination is also a solution. Now, when I wrote this linear combination, there was no particular reason why I chose the 3 and the -4. I just wanted to create a linear combination, so some multiple of e to the 2t, our first homogeneous solution, some multiple of e to the -2t, our second homogeneous solution. So again, there's no reason that I picked the 3 and the -4. It was completely random. But it is a linear combination of homogeneous solutions, so it should also be a solution. So to verify this as a solution, we'll take our original differential equation, y double prime minus 4y equals 0, and let's evaluate this at our proposed solution. So we'll stick it in for y. We'll take its second derivative, and we'll stick it in for y. And we're trying to verify, trying to ask the question, will this equal 0? So like before, let's take our first derivative, and when taking the first derivative, we're going to be leaving one derivative behind. So a first derivative of 3e to the 2t would be 6e to the 2t, and a first derivative of 4e to the -2t would make this be plus 8e to the -2t. On our second term, I'm going to go ahead and distribute the -4 and write this as minus 12e to the 2t plus 16e to the -2t. Now, as is now, these don't cancel. These don't equal 0. But we still have one more derivative to take. So let's take our one more derivative. The derivative of 6e to the 2t is going to be 12e to the 2t. The derivative of e to the -2t would be minus 16e to the -2t. Here we would like to see that this 12e to the 2t will cancel with the -12e to the 2t, and the -16e to the 2t will cancel with the +16e to the 2t, so that this does equal 0 like we were hoping. And we have verified the superposition principle by showing that a linear combination of two homogeneous solutions is also a solution. Now, in future sections, we're not going to want to verify this. We're going to want to be able to say, if I have a first homogeneous solution and I have a second homogeneous solution, then by the superposition principle, we already know this entire linear combination will be a solution. This is going to be an important theorem for us. Okay, let's look at another example. I've given another second-order linear differential equation for you to consider. Second-order linear homogeneous DE. Like our last example, I'd like you to verify that cosine and sine are individually solutions of the homogeneous DE. And then I'd also like you to verify again the superposition principle by showing that a linear combination is also a solution. I'd like you to pause the video so you can work this on your own. I'm going to work this problem as well while the video is paused. So when you come back, you'll see the solution written out. And I really want to emphasize presentation. Duplicate the presentation, the level of presentation that I'm using on our last example. At our level of mathematics, one of the things we want to walk away from is how to present and convey information to others. And if you're working with another colleague, another student, even if their answer is right, but you can't read it because their work is sloppy and unorganized, you're not going to want to work with them. So start to develop these presentation skills that you want to have as a differential equation student. You are going to need these skills in future math classes. So be organized, use colors, use great penmanship, present it cleanly. Okay, I'm going to pause this video. I'll see you back here in a couple of moments. When you come back, you will see the solution already written down. Okay, I'm back. So I wrote out the two solutions for this second order linear DE, y double prime plus y equals 0. And I'm hoping you did the same as well. So right now you're actually going to be just looking at my work and verifying that you got the same result as I did. Of course, it did say confirm or verify the superposition principle, so we should have already known this was going to work. But what I'm asking you to recognize is the level of presentation and the type of work that is required to verify this. So you should have verified that individually cosine and sine produce 0. Individually cosine and sine are solutions of the differential equation. And then also verified that this linear combination was also a solution. And again, I do want to emphasize there's no reason that I picked 2 and 3 to be the coefficients of each of these. It was completely random. I just wanted to pick any 2 values. You can change these to be -2, +5. It wouldn't matter. These would still both be solutions, and this would still be a linear combination. It would be a solution. Okay, let's move on and look at a little bit more here. Now let's talk about the non-homogeneous principle. The non-homogeneous principle. The non-homogeneous principle says, if you are given a non-homogeneous linear differential equation, now remember the terminology, a non-homogeneous differential equation means the right-hand side is not 0. That's what non-homogeneous means. This is not 0. So the non-homogeneous principle says, if UP is a particular solution to the non-homogeneous DE, and we're using the letter P as a subscript here to let us know, to just emphasize that we're talking about a particular solution to a non-homogeneous differential equation. Now, if this is a solution, it means when I evaluate the DE at UP, I get the right-hand side back. Remember, if it was homogeneous, I'd get 0 back. But if it's a particular solution to a non-homogeneous DE, when you evaluate it, you get the right-hand side. We also have UH, notice the H as a subscript, is the general solution to the homogeneous DE, meaning that when we evaluate the DE at UH, we should get 0 because it's a homogeneous solution. So the non-homogeneous principle says the sum is also a solution to the non-homogeneous DE. Meaning if you add UP and UH together, this is still a solution to the non-homogeneous DE, meaning you will still get f of t back. The justification for this should make sense. If you take your particular solution and add it to the homogeneous solution, this should still equal f of t. Now the reason this works is, remember, the linearity property of these linear operators, meaning you can break up the left-hand side, L of UP plus UH, as L of U plus L of H. And this is because we're talking about a linear operator. It has this linear property that the linear operator of a sum is the sum of your linear operators. And then we also have that L of UH, by definition, is 0 because it's a homogeneous solution. So because that's 0, it goes away. And so we end up with just L of UP equals F of T, which we know it will be because we said UP is a non-homogeneous solution. So by definition, we already knew that this was going to equal F of T. Now, what I'm trying to get here with this non-homogeneous principle is that it gives us a method for solving some simple linear differential equations. And I say simple because it won't work for very complicated ones yet, because I haven't gotten that far in our theory yet. I will get there soon, though. So first, what I'd like you to recognize here is I'm giving you a first-order, non-homogeneous linear DE. Remember, this terminology is important. When I say it's first order, we're talking about something with a first derivative. It's non-homogeneous because of the 4, but it's a linear DE because all of the variables y are raised to the first power. There's no square root of y, something like that. So for this first-order, non-homogeneous linear DE, I'm looking for solutions. And the way I look for solutions is I look for them in pieces. I first look for the non-homogeneous solution. And the way I find my non-homogeneous solution is I notice that the right-hand side of my differential equation, the 4, it's a constant. That makes this particular differential equation a little easier to solve. Because the right-hand side is a constant, it makes me want to guess that the particular solution yp is probably going to be a constant also. It's because the right-hand side is a constant, it makes me think yp is also a constant. Now, maybe this isn't apparent yet, but let's go through my example so you can see why. If yp is a constant and we plug it into the differential equation, then we'll have, let me think about how to write this out. Then we'll have y prime minus 2y equals 4. But we're going to evaluate y prime and y at a constant c. So we're supposing it's a c, it's a constant. So let's plug a constant in here. Notice that our first term, the derivative of a constant, well, because this is a constant, the derivative is 0. What this leaves is an equation that can be solved for c. Here I have negative 2c equals 4. I think that would mean that c would have to be negative 2. And this says, well, let's take yp to equal negative 2. Observe that this works. If you plug in negative 2 here, then the derivative of negative 2 would be 0. And then you'd have negative 2 times negative 2 would equal 4 like we wanted. This is a particular solution. Okay, now we look for the homogeneous solution. Now, if we're looking for a homogeneous solution, we're looking for solutions to the equation y prime minus 2y equals 0. And it has to be 0 because we're talking about homogeneous solutions. So even though there was a 4 initially, we turned the 4 into 0 because we're looking for homogeneous solutions. Now, because of the form here, it makes me think of what we did back in chapter 1. Maybe I should write this as y prime equals 2y. Now, you can solve this differential equation by separation of variables, but from recognition of what we did in chapter 1, I want to say there's only one function whose derivative is 2 times itself. And it would be y homogeneous is c e to the 2t. You may want to verify by separation of variables that this is your homogeneous solution. Putting this together, we have the general solution and we should reference this theorem when we do it. The general solution by the non-homogeneous principle I will be expecting you to reference appropriate theorems when we do our exams, so get in the practice of doing it in your homework as well. By the non-homogeneous principle, our general solution should be y of t. It's your particular solution, negative 2, plus your homogeneous solution, c e to the 2t. This is what we're looking for. Now, graphically, I would like you to see why we know, or what this looks like in terms of a direction field. Recognize that we know c e to the 2t are exponential functions. They're increasing exponential functions because of your 2t, your positive exponent. And then also recognize from algebra, we know the negative 2 should do a vertical shift downward of our known function. Hence, we have our solution curves looking like exponential functions that have been shifted down 2 units. So here are a couple of solution curves that I could draw. So get a familiarity with what these solutions will look like graphically. Okay, let's try another example. Let's find the general solution of the following first-order non-homogeneous linear DE. Now, this is very similar to our last example, so I'm going to ask you again to pause the video and look for your general solution to your differential equation. Again, I'd like to ask that you mimic great presentation. Show me how you're looking for your solution by labeling each of the individual parts of your solution. Don't just write the solution. I want you to show me how you're getting the solution in a nice, organized way. So show me how you're finding your non-homogeneous solution. Show me how you're finding your homogeneous solution. Reference the appropriate theorems when you're writing your general solution. So mimic my write-up, please. I'm going to pause my video as well, and I'm going to write out the solution for you so you can verify your work after you're done. I'll see you in a moment. Okay, I hope you looked at this last example on your own and you're ready to just verify your solution. Again, I was asking you to show me specifically the kind of work needed to demonstrate your solution. So I wanted you to show me what your non-homogeneous solution was, and I wanted you to show me how you were finding it. I'm hoping that you verified that your particular solution to the non-homogeneous differential equation was 5/3. I'm hoping that you have found your homogeneous solution. by setting the right-hand side equal to 0, solving for y prime and recognizing the only function whose derivative is a multiple of itself is c e to the negative 3t. Again, you could have verified this by separation of variables. And then written your general solution referencing the appropriate non-homogeneous principle as 5/3 plus c e to the negative 3t. Now again, graphically, what I'd like you to be able to see with this is that c e to the negative 3t is a decreasing exponential function because of that negative exponent. So this has graphs that look something like this. And then the 5/3 from algebra we recognize should do a vertical shift upwards of this decreasing exponential function, which produces graphs solutions that should look something like these. Of course, there are solutions down here that I don't typically draw just because I have a hard time visualizing them. Okay, I have one more example to present with you, and this problem is a little bit different. We have not learned how to solve non-homogeneous differential equations where the right-hand side is a variable. This is something we will talk about still. So in chapter 2.1, there are going to be a couple of problems where they say, verify that this given function yp is a particular solution. They're not telling you where they got it from yet. That'll come in a future section. But right now they're just saying verify that this is a solution to the non-homogeneous DE, and then let's find the general solution. So for this verify part, we want to verify this non-homogeneous solution. So there we have our differential equation, y prime minus y equals t. And we want to show that yp is equal to negative t minus 1 is a particular solution. So again, we evaluate our dE at this proposed solution. So let's stick in the negative t minus 1 for y. And we're asked to show that this is equal to t. This will tell us that this is a particular solution to the non-homogeneous DE. Now, because of the way we take derivatives, the derivative of negative t minus 1 is going to be negative 1. And then the derivative of negative 1, because it's a constant, we know this is 0. Maybe we can distribute this minus sign into the parentheses and write this as plus t plus 1. Notice that the minus 1 and the plus 1 will cancel, and so that this is equal to t like we wanted to, verifying that yp is equal to negative t minus 1 is a particular solution to the non-homogeneous DE. Okay. Now let's find our homogeneous solution. For our homogeneous solution, we're looking at the differential equation, y prime minus y equals 0. So you're forcing that right-hand side to be 0. Of course, following the pattern we've been looking at, we'll solve for y prime by putting the y onto the other side. And again, you can do the separation of variables, and I encourage you to, but sometimes I want you to just recognize solutions of differential equations. You don't have to write them out every time. At some point, you're okay to say, I recognize my solution. In which case, I'd like you to say YH, and use the H to represent your homogeneous solution, has to be CE to the T. So here we have a homogeneous solution. Here we have our particular solution. So we'll end by saying, by the non-homogeneous principle, the general solution is y of t equals negative t minus 1 plus c e to the t. Now, it might be fun for you to verify this is a solution. So I'm going to stop the video here, but if you want to do a little bit more work, just to verify that this is true, it might be nice to actually evaluate all of this into the differential equation to verify this really does still equal t. So I'm going to stop the video, but what I'm encouraging you to do is to take our differential equation y prime minus y equals t, plug in the negative t minus 1 plus c e to the t, in for y, take the derivative, minus negative t minus 1 plus c e to the t, and verify that this all still equals t. But do this on your own. Okay, this should give you everything you need for your homework for Chapter 2.1 on linear differential equations. I'm sure we'll be able to talk about this a little bit more during our virtual class session we'll hold, but I hope this is enough to get you through your homework. I'll see you next time.